10.1, where we will talk about systems of linear equations in two variables. So every systems of linear equations are basically looking at whether two lines intersect on a plane or not. So for example, if you have in real world applications, if you have an equation, a linear equation for supply and a linear equation for demand, then typically analysts want to know where the supply and demand equal each other. Okay? Operating beyond that point has certain implications. Operating below that point has certain other implications for a business. Okay, so this is about that. This section is all about that. So there are three main cases for solutions of systems of linear equation. One case is if the system has one unique solution. In other words, if the two lines, in this case 3x plus y equals 1 and 5x plus 2y equals 1, intersect, those two lines intersect each other at one unique point. And I should mention that the methods that we use to solve these systems are called the method of elimination and the method of substitution. In this section, we will use those two. And in the next section, in section 10.3, we will talk about a new matrix-based method called the Gauss-Jordan method of solving a system. So generally, why do we have these different methods? Well, generally, if you have a small system like this, 3x plus y, just like the one that you see on the screen, like that one, then the method of elimination and substitution works just fine. But the bigger the systems are, particularly if you have a system of 4 equations and 4 unknowns and systems that are bigger, then elimination and substitution becomes very, very laborious. And at some times it becomes unmanageable. But the matrices, the bigger the system is, it makes no difference. It still works just as fine as when you solve a smaller system like that. So just keep in mind, for larger and larger systems, definitely the Gauss-Jordan method is the way to go. Okay, so the method of elimination and substitution, they're really pretty much the same method. But if you say the method of elimination, if you say that's what you're using, that means you're first eliminating a variable, then you substitute in the equations to find the other variable. If you say you're using the method of substitution, then you are first substituting and then eliminating the other variable. So it's just that the two methods are very, very close and intermingled with each other. But the Gauss-Jordan is totally different method. In the Gauss-Jordan method, which we will look at in section 10.3, you don't use the variables, you use their coefficients. The other thing that you should know right from the start is that whether you use the Gauss-Jordan method, which we will look at in the future, or if you're using the method of elimination and substitution, the way you order the variables and the constants must be the same. So, for example, in this case, notice how both variables for which we're solving are on the left, and the only terms that are on the right are the constants in both equations. Okay? The other thing you should notice is the order of the variables. So if you have two variables like this, then you should order them as x first, then y. If you have x, y, z, then you should order them in as x, y, z. And suppose for bigger systems, if you have x1, x2, x3, x4, x5, then you should order them in the system in that way, with all the constants or the constant on the right-hand side. Okay, so the order in which the variables appear is very important in this method. The constants should always be on the other side. And it goes the same way with the Gauss-Jordan method. Okay, so these are the fundamental things we should know right from the start. I'm pretty sure all of you have seen or solved systems before, so this will be a nice review. But in any case, please remember to skim through the textbook before you watch this video or you attend the class. Then watch the video and attend class while taking notes of the questions you might have, and also writing down anything that you think is particularly important for you. Write those down as they catch your attention. And of course, you review those lecture notes that you took in class or during or when you watch this video, and go over the problems that I solved once again without looking at the solutions to see if you can repeat those solutions. And of course, complete all the homework assignments by the due date. And throughout this course, I'm sure you're finding out now that as we approach the end of the semester that reviewing material was very important, because otherwise the material would not stay in your mind. Not you, but anyone, myself included, we tend to forget if we don't go back to these previous material and take a look at them again. Okay, so having talked about that, here's a fully solved example that I already have for case 1 of a system that is a system that has one unique solution. So I'm using the method of elimination, which is you determine which one of these two variables you'd like to eliminate. It doesn't matter which variable, as long as you do it the correct way. You can either choose the x variables to eliminate or the y variables. And once you eliminate one of the variables, you can easily solve for the other variable. And then you use that variable to plug back into any of these original equations and solve for the variable that you eliminated in the beginning. So here I'm eliminating the y terms, and the reason I chose that, is because I'm looking at the coefficients here, and the coefficients of y, variable y, are easier to deal with. So that's the only reason. So I multiplied the top equation by a number that I knew would give me a coefficient equal and opposite to positive 2. So as you distribute the negative 2 into this whole equation, right, what do we get? We get this bottom system, minus 6x minus 2y equals minus 2, right? This minus 2 gets distributed into the full equation. Then the bottom equation stays the same as before, and all we have to do now is add these two equations. Okay? When you add them, the y terms get eliminated, right? As we intended. So minus 2y plus 2y adds up to 0. Then minus 6x plus 5x, you get minus x, equals minus 2 plus 1 is minus 1. So you solve this equation, which is an equation, linear equation in one variable, for x, and you get 1. Okay? So x equals 1. Now, substituting this x equals 1 into any of the original equations will help you solve for y, for the other variable, the variable that we eliminated. So that's what I did. I substituted this x equals 1 into the first equation in the system, that one. So you can see 3 times 1 plus y equals 1, and then when we solve for y, we get the full solution, which is that. So this point, which is the solution of the system, means that those two lines intersect at this point, 1 comma negative 2. So these two lines intersect at 1 comma negative 2, which is the solution of the system. So let's look at this on the computer. So one of those equations, I'm just going to enter them here, was 3x plus y equals 1, right? There it is. Let me zoom in like that, right? And then the second equation in the system was 5x plus 2y equals 1, okay? So look at the blue, where the blue line and the red line intersect, and let me zoom in like that. So you can clearly see that point as being the intersection point, and that is the point, intersection point that we found, which is 1 comma negative 2. You see that? That green dot, let's snap to it with the coordinates there. 1 comma negative 2. So solving a system that has a unique solution means finding the intersection point of those two lines. Okay? So that's what solving a system means. Okay, so let's go back to our dot camera here. Here is case 2. Case 2 is when a system has no solution. This is when two lines do not intersect. In other words, if the lines are parallel, then they do not have any solutions. So let's see how this works. I'm going to use the method of elimination like before. So looking at these coefficients, I'm thinking that the easiest variable to eliminate would be the variable, maybe the y term, right? Actually, either one. So let's multiply the bottom equation by positive 2. Okay, what do we get? We get the top equation stays the same. The bottom equation, let's distribute the 2 into that. 2 times minus x, minus 2x. 2 times plus 3 halves y, plus 3y, right? 2 and 2 cancel, you get 3y, equals 8 when you distribute 2 into the other side, right? So now we're going to add these two equations. What do we end up with? Well, 2x plus minus 2x adds up to 0. Minus 3y plus 3y equals 0. On the other side, what do we have? 12 plus 8 is 20. So what do we end up with? 0 equals 20. Is this even possible? This is an impossible result, right? This is impossible. So that means that those two lines do not intersect. They are parallel lines. So there is no solution, and the lines are parallel and never intersect. Okay? So that's our final conclusion here. So let's take a look at the graph of these two. Let's go back to the computer. So we want to use this to see exactly how this turns out to be. We have 2x minus 3y equals 12. And then the other equation is minus x plus 3/2 y equals 4. Looks like I need to zoom out to see. There you have it. There you have both lines. Okay, the purple and the black line. Look at them. They are parallel. They never intersect. We can zoom out as much as we want. Now we're too far out, so they're beginning to look like as one single line, which they're not. But it suffices for you to note that when two lines are parallel, they do not intersect. Therefore, there is no solution to the system. Okay. So let's go back to the dock camera. Okay. So the other thing that I hope you noticed is that look at the order of the variables. The x first and then the y. The variables are in the proper order, and the constants were on the right-hand side of the system. So whether you're using this method of elimination and substitution or the Gauss-Jordan method, you must make sure that the variables are in order and the constants are on the other side. If they're not, you have to put them in that order before you begin solving them. Okay, so case 3 is when we have infinitely many solutions. This is the opposite of example or case 2. So how do we get infinitely many solutions? That means the lines intersect each other at infinitely many points. How is that even possible? The only way that is possible is that if the two lines are the same line, they overlap completely along their full length. So at every point along their length, they are one and the same line. They intersect because they're the same line. They lie on top of one another. Okay, so let's solve this and see how we get to that conclusion, because the conclusion that there was no solution is when you end up with 0 equals some number like 5 or 20. So obviously you can't have that, right? So let's see what kind of a conclusion or result we get when we try to solve a system like that. Okay, so we have, looking at these variables, I'm thinking that x is an easier variable to eliminate. So I'm going to multiply the bottom equation by minus 6, because I know once I distribute minus 6, I get minus 12x as the coefficient of x, plus 12x, they add up to 0, right? Okay, so the top equation for now stays the same, 12x plus 15y equals minus 18, minus 12x minus 15y, right? When you distribute minus 6 into 5 over 2y, minus 6 times 5 is minus 30, divided by 2 is minus 15y. And then let's not forget to distribute the minus 6 to the other side, and that'll give us positive 18, right? Minus 6 times minus 3 is positive 18. So now we're going to add the two equations. Okay, so 12x plus minus 12x, they add up to 0. 15y plus minus 15y, they add up to 0. Minus 18 plus positive 18, they add up to 0. So what do we end up with? We end up with 0 on that side equaling 0. No one can argue with that, right? 0 equals 0. So, but notice that this final equation, I mean, if I bring back that old one, see, when we looked at the first example or the first case when there was one unique solution, notice after you add the equations, we ended up with an equation with one variable which we had to solve for, right? And x equals 1. But notice that here, even though the equality is not contradictory, 0 equals 0 always. But the other thing that should catch your attention is that notice that in this result, there is no variable. Either x or y are not present. That means this result does not depend on either x or y. This result is always true regardless of those two variables. That means that the two lines are literally the same line. Okay, if I graph that, you're not going to see two lines. You're going to see one line, just one line. As a matter of fact, we can just go to the computer, and so before we do that, so let's conclude this result and say that this is true at all times, thus the two lines overlap completely, and we have infinitely many solutions. Infinitely many solutions, okay? So let's graph these two lines on the computer. So one of those lines was 12x plus 15y equals minus 18. And the other one was 2x plus 5/2 y equals minus 3. I mean, look at it. Before I did that, see, here's the red line, which is the equation you see there. But as soon as I enter minus 3, the blue line appears, and it is overlapping the red one completely. There. You see that? So it overlapped the red line completely. So the two lines are the same. And therefore they intersect each other at infinitely many points along their length. Okay, so let's go back to the dock camera. So I have a few examples here for us to solve. This one, I highly encourage you to please pause the video. We have 3 examples left, number 3, number 4, and number 5. As you know, the blank worksheets are posted on Canvas. Download the worksheet for this section, 10.1, and solve these last 3 problems on your own without watching the video first. And then when you're done, then come back to the video and see how I answered it. Okay? All right, so I'm assuming, I trust that you did that, and I'm grateful that you did that. And now, let me show my solution, and hopefully your solution and mine agree. Okay, so here, first thing I check very quickly in a second, just to make sure that the variables are in the proper order and the constants are on the right-hand side. They are. So everything is good. So now I'm going to see what I can do to eliminate variables. Looking at the coefficients, the y variables are already equal and opposite in algebraic sign. So without doing anything, I can certainly, I can right away add these two right away and eliminate the y terms. Let's do that. So the y terms drop out or add up to 0. 2x plus x is 3x equals 16 minus 1 is positive 15. So x equals 15 over 3 because we're solving for x, which means we need to isolate x. So we divide both sides by 3 to get rid of what's next to it. So that'll be 5. Okay? So that's the solution for x. Let's see where the y is. So either you can plug this 5 back into either equation. I usually pick the equation that I think is easier to work with, which is the bottom equation in this case. So using x minus 2y equals minus 1, let's substitute with x with 5. So we have 5 minus 2y equals minus 1. Minus 2y equals minus 1 minus 5. Minus 2y equals minus 6. Right? And then y is equal to minus 6 divided by minus 2. Right? We're solving for y, so we need to isolate y. That means we need to get rid of the negative 2. So we divide both sides by negative 2. Negative divided by negative is positive, so we end up with positive 3 for y. So we have the x, we have the y, and the solution is 5, 3. Okay, so that's the solution of the system. Let's go back to the computer and plot this system and make sure that 5, 3 is in fact where they intersect. So we have 2x plus 2y equals 16. X minus 2y equals minus 1. So let me zoom in on that. Clearly they intersect at some point, right? So we can snap to that intersection point with the point that the solution we found, which is 5, 3, right there. It snapped to it, and let's label it. And there you have it, 5, 3. Right? We can even zoom into it even more, like that. Okay, so let's go back to the dock camera. I hope this solution agreed with what you had. Number 4, we have this system. Once again, I look at the coefficients and to see which coefficient or which variable is easier to eliminate. So I'm looking at the x terms are easier to eliminate. So I'm going to multiply, just looking at the coefficients, right? All I have to do is multiply the top equation by a number to give me an equation and a coefficient of x variable in the top equation that is equal but opposite in sign when compared to the coefficient of x in the bottom equation. And that would be minus 2. Right? So we're going to distribute negative 2 into the top equation. So we have minus 8x plus 6y, right? Minus 2 times minus 3y is plus 6y. Let's not forget to distribute the negative 2 to the other side. Minus 2 times 24 is 48, right? Minus 48. So the bottom equation stayed the same for now. And let's add these two equations. So minus x plus 8x adds up to 0. Positive 6y plus positive 4y, we get 10y, right? Minus 48 plus positive 8, we get minus 40. So we need to we're solving for y, so we need to isolate y. And 10 right now isn't allowing us to isolate y. So divide both sides by 10 to get rid of it. So y equals minus 4, right? Minus 40 divided by 10, minus 4. So that's one of the variables. let's plug this y value into either one of those first equations and solve for x. I think the bottom equation is easier to work with. You might disagree with me, which is fine. You can use the top equation. You would still reach the same result. So using 8x plus 4y equals 8, let's plug in for y with negative 4. So we have 8x plus 4 times minus 4 equals 8, right? So we have 8x minus 16 equals 8. 8x equals 8. Send this minus 16 to the other side of the equality symbol. It was negative on this side. When you move it to the other, it becomes positive 16. And so 8x equals 24. And therefore we have x. We're solving for x, so we need to isolate x. We need to get rid of the 8, which is preventing us from isolating x at this point. So divide both sides by 8, we get 3. X equals 3. So we have x equals 3 and y equals negative 4. Let's put them together. We have 3 comma negative 4 as the solution of this system. Okay, so let's look at the computer graph, and what the computer graph should show us is that in fact these two lines intersect at that point. Okay, so we have 4x minus 3y equals 24, and 8x plus 4y equals 8. Right? There's that point. Can I zoom in a little more? Maybe we can. Well, that's too close, I think, like that. So let me snap to that intersection point to make sure that is 3 comma negative 4. Right there. 3 comma negative 4 snaps to that intersection. So the two lines indeed intersect each other at 3 comma negative 4. So these two lines are totally different lines, right? One of them is sloping uphill or has a positive slope. The other one has a negative slope, the blue one. But at one point, they agree with each other. They have the same solution. And that point is the point at which they intersect. That's the whole point behind solving a system. To see at which point these lines that are doing this a thing of their own, at which point they actually agree with each other. Okay? Okay, so let's go back to the dock camera. Now we have a system, and it says, solve the system if there are infinite number of solutions. Enter the general solution in terms of x, where x is any real number. So, what do we expect to see if there are infinitely many solutions? If there are infinitely many solutions, what we would expect to see is an equation with both sides equal to each other, such as 0 equals 0, 2 equals 2, 5 equals 5, something like that, right? So if there are infinitely many number of solutions. So let's investigate that, because we don't know that yet. So looking at these numbers, I'd rather eliminate the y variable because it has smaller coefficients. So I need to use smaller numbers to get rid of the y variable, whereas with the x, the numbers are larger. So let's multiply. Well, let me rewrite this here because I don't have enough room up there. So 10x plus 4y equals 16, and 15x plus 6y equals 24. Okay, I'm going to eliminate the y terms. So I'm going to multiply the top equation by minus 3 and the bottom equation by 2. Because that when you distribute this into the full equation and the 2 into the full equation, with the coefficients of the y variables become negative 12 and positive 12, which means I can add them and eliminate the y variable. Okay, so that's my plan at least. Okay, so distributing the negative 3 into this, we get negative 30x, negative 3 times 4y, negative 12y, equals minus 3 times 16 minus 48. Right? Now distribute the 2 into the bottom equation. 2 times 15x, 30x. 2 times positive 6y plus 12y equals 2 times 24, positive 48. So now let's add the 2 equations. What do we get? Well, we get negative 30x plus 30x, 0. Negative 12y plus 12y, 0. Equals negative 48 plus 48, 0. So in fact, we get a scenario where there are infinitely many solutions. We just verified it. So there are infinitely many solutions. Okay? So they say if there are infinitely many number of solutions, which we verified that there are in fact that, enter the general solution in terms of x, where x is any real numbers. Okay, so then in this case, we need to have what they're asking us is that, okay, the solution x comma y for these infinitely many solutions, write this solution in terms of x. So x is already x, so we don't have to do anything here. But y, we need to write y in terms of x. That's what it means when it says enter the general solution in terms of x, where x is any real numbers. Okay, the general solution. So x is x. Let's write y in terms of x. So we can write y in terms of x using any of these 2 equations. You can choose either one. Makes no difference. I'm going to pick the first one. So using that first equation, using 10x plus 4y equals 16, let's solve this for y in terms of x. So we have 4y equals 16 minus 10x. We're solving for y, right? So we need to isolate y, and the 4 is preventing us from isolating y. So we need to get rid of the 4 by dividing both sides by 4. So y equals 16 over 4 minus 10 over 4x. Now let's simplify. Y, 16 over 4 is 4 minus 10 over 4 is 5 halves x. Okay? Or you can leave it like this, or you can put this first and say minus 5 halves x plus 4. It makes no difference. So that is why, and that x is x. So the general solution in this case will be this. Parenthesis x comma, instead of y, 4 minus 5 halves x, close parentheses. So we now have the general solution for this system written in terms of x, where x, let me add, where x is any real number. Okay. All right. We have come to the conclusion of another section, 10.1 in this case. I hope you have been following my advice of solving these problems on your own without looking at my solutions and then checking your solutions with the ones I show in these videos or in class. Okay. So for now, have a very nice day, and I'll see you all again next time.